Okay, good news on, there's some good news for Maclaurin series, and that is we are going to use a table 1, which is of known Maclaurin series. And remember, Maclaurin series were Taylor series, but they were Taylor series centered at a equals 0. So if we want a Maclaurin series and we can match it up with one of these known Maclaurin series, then we don't have to go through the whole process of finding the Maclaurin series. Actually, last time I think we did do this one, maybe one similar to that one. But good news is we can use this table to help us along. Just, and matter of fact, does this one look familiar? Yeah, that one's the one we started this power series stuff with, basically, and so now we've just expanded our known ones out here. And so we're going to use these just like we use this one. Like if I had 1 over, what would I do if I wanted 1 over 1 minus x squared? Well, if I wanted 1 over 1 minus x squared, I would just say, well, x is x squared, and so I would replace x here by x squared, and that would give me my Maclaurin series, right? My power series. And so we're going to use that. So it's got several others. I didn't take the time to write those out, but this is good news. We can use these to our advantage. And I will have these provided. You won't have to write these on a note card or anything. I will have these provided on a table available to you. So let's use one or two of those. Okay? Write f of x equals e to the 3x as a Maclaurin series using a series from table 1. Well, this turns into a nice, easy little exercise because e to the 3x equals, since I know from table 1, I know e to the x was what? The sum n equals 0 to infinity x to the n over n factorial. That's from table 1. From table 1, I know that e to the x is the summation x to the n factorial as a power series. So e to the 3x would be what? Well, instead of x, I got 3x. So instead of x here, I'm going to put 3x. So it would be the series n equals 0 to infinity. So instead of x, I've got 3x to the n over n factorial. And unless there's some canceling or combining, that's all I need to do with that. We got it. Essentially, the work to show that this is the Maclaurin series has been already done for us, so we'll just tag along for the ride there. Okay, right, here's another one. Write the Maclaurin series for f of x equals x cosine of x squared using the table 1. All right. Well, obviously, we want to look at our Maclaurin series and see what we've got there on that table. Well, we have on the table 1, we have the cosine of x is the Maclaurin series. What is it? Negative n equals 0 to infinity. Negative 1 to the n, x to the 2n over 2n factorial. That's what cosine of x is. So how do I use that here? Well, in this case, I want x cosine of x squared. And so I can use this power series to replace this. So it's going to be x times, well, instead of x, I've got x squared. So it's going to be, the series is going to be n equals 0 to infinity, negative 1 to the n. And so instead of x, I've got x squared. So I replace x by x squared. Well, that would be n equals 0, negative 1 to the n. What would that be? X to the 4n? X to the 4n over 2n factorial. And then what else did we do? What would we do with the x here? Well, that being x to the 1, if I bring it in, it comes in on this, and what do I do? What happens to that term right there? Yeah, it adds to it. So it would be the power series n equals 0 to infinity, negative 1 to the n, x to the 4n plus 1 over 2n factorial. Okay? So as far as evaluation, this is pretty easy because we're just using the table there to substitute in on. Let's give it one more try on this one. All right, write the Maclaurin series for f of x equals x to the 4th times the tan inverse of pi x using table 1 and of course I should mention here, you know, if it wants me to find it, you know, going through the regular Maclaurin series stuff, which is, you know, that's the doing the nth derivative thing, it will probably so state, but most of these we're going to say use table 1 or using a known Maclaurin series or something like that. Okay, well, it turns out, believe it or not, there is a tan inverse one on that table, isn't there? From table 1, we know that the tan inverse of x is the series n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1. That's what tan inverse is. Well, in this case, I want tan inverse of pi x and then times it by x to the 4th. So let's see what that gives us. So x to the 4th times tan inverse of pi x would be x to the 4th times the series n equals 0 to infinity, negative 1 to the n. But instead of x, I've got pi x. And that would be to the 2n plus 1 over 2n plus 1. Now what might you see we'd want to do there? With this x to the 4th hanging out here, I might want to bring it in. And so I can't just add it to that because it's pi x instead of x. And so I've got to split those out, so to speak. Make it pi to the 2n plus 1 times x to the 2n plus 1 over 2n plus 1. Right? Then I can bring this x to the 4th and tack it in with the x to the 2n plus 1, which it would just add on to that, wouldn't it? X to the 4th times x to the 2n plus 1. We just add in there. Be 2n plus 5. Does that sound right? Believe that? Okay. We are going to talk here about a couple of integrals. And the thing on this integral here, is that all right? Any further question? We got that one. I may have mentioned this before, but one application of Taylor series, power series, involves integrating certain functions. This is an impossible function to integrate. You can't integrate this by U substitution, by parts, by anything we've ever talked about. And there's nothing whatsoever, trig substitution, anything we try would not work. It's an impossible one to do. However, with Taylor series, at least we can get it down to stuff we can integrate. Because remember, on Taylor series, what we wind up with basically is a polynomial with maybe a factorial thrown into the mix. And so this is going to be one application, I guess you might say, of power series, doing integrals that we can't do any other way. All right, so we're going to evaluate this. The way they'll state it is evaluate the integral as an infinite series. Okay, well, what I need to do then, what does that mean? I need to write e to the minus x squared as a power series. And I guess depending on where you want it to converge would make a little difference. But here, if I just use our Maclaurin series, the table 1 Maclaurin series, this is not too bad to do that, is it? We've already done one with an e to a power. Here's another one. E to the x was, I don't have it memorized, n equals 0 to infinity, x to the n over n factorial. That's what e to the x is. So e to the minus x squared would be, well, it would be, instead of x, I've got minus x squared, so that would be power series wise, negative x squared to the n over n factorial. With me on that? Just replacing x by x, minus x squared. And so that's negative, series negative. 1, let's say negative 1 to the n, x to the 2n over n factorial. Which, okay, so I want to evaluate this, I want to integrate this. Well, integrating that, I guess we could. But in the assignments, the answers, they'll probably write this out term by term because I'm going to evaluate it term by term is one way they go at it. But let's see. All right, so start at n equals 0, so we have negative 1 to the 0 is 1, x to the 0 is 1, 0 factorial is 1, so the first term is 1. N equals 1, we have negative 1 to the 1 be negative 1, x squared over 1 factorial is 1, so it'll be x squared, negative x squared. And then the second, n equals 2, we'd have positive 1, x to the 4th, and then 2 factorial, which is 2. So it's x to the 4th over 2. Then n equals 3. Yeah, I did it out to 3, to n equals 3. So n equals 3, I would have negative 1, x to the 6th over 3 factorial, which is 6. So it's negative x to the 6 over 6. And then you can keep that going. All right, so back to this then. So the integral then of e to the minus x squared dx would be the integral of this series, which turns out to be this. So that's kind of how they'll denote it here. Which you see is something we can do, right? We can do the integral of that, because this is just power rule antiderivative, isn't it? What's the antiderivative of that? The x. What's the antiderivative of that? 1/3 x cubed. Antiderivative of that? It'd be 1/2 times 1/5 x to the 5th minus 1/6 1/7 x to the 7th. One other thing. That's going to keep going. But there is one other thing. This is an indefinite integral. What else do I need? A constant, don't I? And since that keeps going infinitely, they usually put the constant up front here. So it's c plus x minus 1/3 x cubed plus 1/10 x to the 5th minus 1/42 x to the 7th. And there's various ways you can do it. Don't forget your constant, because we're doing the indefinite. Yeah, just go so far. Now, one other thing they might throw in is what would be the nth term here? The nth term. Well, the nth term I could get, couldn't I, just by maybe doing the antiderivative of that, because really I'm doing with respect to x, so this is just a constant. And so my nth term would be negative 1 to the n factorial, times what would be the antiderivative of that? Well, you're going to add 1 to that. And then divide by the 2n plus 1 new power. What's that?
Since you're starting at 0, 0 would be n equals 0 is your first term. So you'd have to do n minus 1 to get the nth term.
No, 0 factorial is 1, so you don't have a 0 denominator. It's okay. You don't have a 0.
But like if you wanted the 12th term, say, when you had to plug in 11 for n.
If you wanted the 12th term, yeah. But it starts at n equals 0, so yeah. Anyway, what I was saying is this, so we could tack this in. We could say, well, this is going to be my nth term. I don't know if they'll include that in your answers, but if you see that, that's all they did. They just did the antiderivative of this guy right here to get this nth term. It would be in the middle, so to speak. Let's see, that would be 2n plus 1. That would be times that. And then, but that's just the nth term, so it keeps going after that. Just FYI.